好，同学好哈。那我们继续第7章的第2部分7.3、7.4。7.3的部分我们会先讲 quarter wavelength transformer 还有 single stop matching 这两个最基本的阻抗匹配技巧。然后我会先跳到7.4哈，所以今天的第2堂课我们会讲 Smith chart 的基本程序。那 double stop matching 还有 bandwidth 的 discussion 我们会等7.6教完之后再回来看哈，以免时间不够哈。不过因为 quarter wavelength transformer 跟 single stop matching 其实都跟 Smith chart 的基础应用息息相关哈，所以我们就把它们合在一起啊。Okay, so let's begin with our discussion with transmission line matching. And as we have seen in the previous lecture that if there are standing waves on the transmission line, what is the cause for the presence of the standing wave? Well, most likely the cause for the standing wave is because you have an unmatched termination. That is, the impedance of the termination is different from the characteristic impedance of your transmission line. So what is the consequence? Well, you get standing wave patterns. Well, the direct implication of not having a matched termination is some of the signal power is rejected, is reflected, is not delivered to the next stage. So it's a waste of energy, It's a loss of your transceiver's efficiency. So in general, we would like to minimize the mismatch in the transmission line system. The other cause or the other reason is, in the current electronic industry, which involve thousands and tens of thousands of companies. Each company may make only 1 or 2 components. So when you try to design or when you try to manufacture a transceiver wireless communication system, you may acquire components manufactured by different companies. And if the components, the input impedance and the output impedance of the components manufactured by these companies have different characteristic impedance. Well, have impedance other than 50 ohms, then you will have to mitigate, have to reduce the difference of those non-15 ohm components. So which will make the design process more complicated. So in general, everybody tries to come up with components that has input impedance and output impedance as close as to 15 ohm as possible, so that people can use your components with ease. But in reality, sometimes you need to adjust, you need to adapt. Well, for example, some components cannot be made as 50 ohms easily. So sometimes you need to try to reduce the difference or mitigate the problem. So in section 7.3, we will introduce a few techniques that can realize the goal of impedance matching. 阻抗匹配，实现阻抗匹配的方法。那basically we will introduce 3 types of matching circuit technique, which are quarter wavelength transformer, single stop matching, and double stop matching. So we will discuss about that in this lecture. So In the previous lecture, we have observed that if you have a mismatch in your termination, you will have a non-zero reflection coefficient gamma, like this. And because of the propagation delay of the transmission line, the non-zero reflection coefficient will modify the impedance observed on the transmission line system. And this impedance will be a function of position L. That is the distance from the load. And we know that Z in will be a number that can be greater than Z sub 0 or smaller than Z sub 0, or it can be turned into a complex number. So to realize impedance matching, what we have to do, we need to reduce gamma L, have gamma become as small as possible. Another problem with the reflection coefficient is the reflection coefficient gamma is a function of frequency. Okay? In this expression, we only see that gamma is a function of position, but it's also a function of frequency. Why? Because in the composition of this expression, it's gamma r times exponential minus j 2 times beta L. And the parameter beta comprise description about frequency by itself. Why? Because beta equals to what? Because beta equals to 2 pi over lambda. And it can be substituted as omega, V over V, okay? So that will be 2 pi F over V. So it contains the description of frequency, which means the reflection coefficient viewed at a different frequency are different numbers. So that the input impedance Z in is also a function of frequency. It becomes a number sensitive to the change of frequency. So, in other words, the transmission line response is sensitive to the change of frequency. As a result, the transmission line, the signal passes through the transmission line will become the so-called dispersive. So what is the meaning of dispersive? Not homogeneous, not the same, or they are different due to the difference in frequency. So one example is rainbow, or the diffrauded colors, the separation of different color where you have a white light going into a prime. It ends up with different colors of different lights of different colors will have different refraction angles. So this is an example of dispersive property. 多写了一个字啊，应该是这样吧 ，dispersive。Okay, so if the reflection coefficient, if the input impedance are function of frequencies, that will make your signal becomes dispersive, which will ends up in degradation of the system performance 会让系统的效能变差也就是说你的讯号过去的时候会出问题啦那当然我们可以再讲。And another thing that the textbooks remind us is the variation is proportional to the length of the transmission line, which means the larger the transmission line, the greater or the more sensitive the response of the transmission line in terms of the frequency change. On the other hand, if the frequency difference is large, the phase difference will become large as well. So equation 7.40 shows that the difference in the ratio of the difference in frequency is proportional to the ratio of phase change. So as a result, the change in the number of wavelengths is proportional to the size, the length of the transmission line. And as I already told you that the variation in the input impedance with respect to frequency will limit the performance of a transmission line system or wireless communication transceiver system. So for this end, for this reason, we need to eliminate, we need to reduce the amount of standing wave so that to maintain a good performance for the transmitter, So here are some 简单讲了就是说，假如讯号中各频率看到的输入阻抗不同的话，那个讯号的波形就会快速的垮掉比如说一个例子，你们都看过的，假如我们有一个方波，方波它的组成是什么？1倍频的 sinusoidal wave 加上1/3的3倍频加上1/5的5倍频嘛所以你看到它的频率的组成是涵盖 fundamental mode 跟它的高阶模态嘛那所以频率差异其实蛮大的，所以他们在传输线系统里头，假如那个大家受到的 attenuation 衰减不同的话，那方波很快就会垮掉。你们现在是3上嘛，所以应该还没有人说过讯号与系统吧？还是讯号与系统刚好跟这门课对开？跟这门课对开的是什么？通讯系统嘛。OK， 那讯号与系统，我不知道你们有没有讲到眼图了 ，I diagram， 意思就是说，本来我是一个像这样的 square wave， 那假如你进到一个 dispersive 的一个传输线系统的话，那通常啦，高阶的成分会被抑制的比较厉害，也就是说你的5倍频、7倍频、9倍频会死得比较快，所以经过一段距离的传输之后，你在接收端看到的波可能长这个样子。那你大致还是可以判断说，这里是0，这里是1，这里是0，这样 OK 啦。那假如走的讯号多一点的话，那就有1有0，有1有0嘛，所谓眼就是所谓的眼图就是这些线交集起来的那个中间的那个区域所以只要还有洞还在你都可以说我们大概可以解调变还解得出来但是假如那个眼闭起来了你就可能不知道它到底是0还是1了所以一般在通讯系统里头，我们会用 I diagram 来去看说这一个通讯系统它传输的极限到哪边那它的这个效能呢，其实也牵扯到我们前面讲的传输线的阻抗匹配的这一个特性 好，你阻抗匹配的好 ，dispersive 的那个 dispersive 的那个程度越轻的话，那当然你的通讯讯号的那个传输品质会比较好。OK， so so in this plot we see a conventional transmission line system. You have generator on one side and the termination on the other side. And if the impedance, if the input impedance of the load is different from the characteristic impedance of the transmission line Z sub 0, we can apply a matching device or another section of the transmission line system to mitigate, to reduce the difference so that the input impedance looking from the left toward the right is the same or as close as Z sub 0 as possible. So that this is the purpose of the matching device. It hopes to change the input impedance of the transmission line with certain determination into the same to become as the same as the characteristic impedance of the line. So if you can accomplish impedance matching, it's the direct implication of impedance matching is you can have maximum power delivered to the load, providing that this is a lossless transmission line system. Okay, and usually you can apply a complex conjugate of the generator internal impedance to accomplish that for maximum power delivery. Okay, so here are the three kinds of matching device or matching technique we will introduce here. The third one is kind of a variant of the second one. And A and B, the quarter wavelength transformer and single stop matching, is probably the most commonly seen matching circuits that you can have on a transmission line system. All right, so let's take a look at the quarter wavelength transformer first. Okay, so in this slide is the basic configuration for the quarter wavelength transformer. So you have an termination of ZR. ZR can be anything: short circuit, open circuit, resistive termination, or reactive termination. No, you can be anything. And you have two sections of transmission line. Now, this is the first section. This is the second section. In general, the first section, well, you have the third section on the left. In general, the first section and the third section are of the same characteristic impedance of your transmission line system. So they are all marked with Z sub 0. And in the middle is the quarter wavelength transformer. The characteristic impedance of the quarter wavelength transformer is different from Z sub 0. It's different from Z sub 0. So it's unknown. The thing that we know about a quarter wavelength transformer is quarter wavelength. The length of this piece of transmission line is about 25% of one wavelength of your interested frequency or your designed frequency. So here are a few parameters that you can play with. Not play with. There are a few parameters involved in this circuit. The low termination, which is known, which is usually known, 你知道的哈。The length of the second section, which is known as quarter wave length. The length of the first section is unknown, so we use dq here. dq, yeah, okay. The second unknown is the characteristic impedance of the transformer. Okay, the rest are known, but these two parameters are unknown. What is our design goal? Our design goal is to ensure the input impedance looking from the left of this dashed line is, which is z sub 1, it must equal to z sub 0. Now, if this is the case, then we accomplish the goal of impedance matching. Oh, so here is the solution. You can have a sneak preview about this problem. Well, okay, but before we talk about the solution, so here is Z1 is the input impedance looking from the left of this dashed line. The other parameter is Z2. This is the input impedance looking from the right of this dashed line. Okay, now because at first we do not have the quarter wavelength transformer, we don't know where to put the quarter wavelength transformer, and we observe the input impedance on the line, that is Z2. So if you change your position, you will have different Z2. Okay, but we will determine a good location, that is the length of dq, and connect it with a quarter wavelength transformer so that the Z1 looking from the left of this connection equals to Z sub 0. Okay, so this is what we going to do, what we want to do about this transmission line matching problem. Okay, so what is how to determine the position of dq, how to determine the impedance of zq. Well, in section 7.2, we know that the reflection coefficient is rotating on the complex plane as it moving on the transmission line. It rotates 360 degrees for every half a wavelength. And in its 360 degree revolution, it will encounter 2 points which it has real input impedance, which the input impedance are real number. And it only happens when the phase of the reflection coefficient is 0 degree or 180 degree. So at this point, the input impedance will become a real number and is greater than Z sub 0. And on the other side, at the opposite of this point, you will have an input impedance that is a real number and is smaller than Z sub 0. And we know that the product of the two input impedance will become what? The square of Z sub 0. So we are going to use this property. So the design is kind of straightforward, starting from the d equal to 0 position, starting from the termination. And if we move along the transmission line, that is move toward the left, then the reflection coefficient on the complex plane will rotate clockwise. So at this position, it will reach voltage maximum, it will reach its maximum input impedance, and it's also a real number. Okay? Then, so this input impedance we see here is Z2. Okay? Then we connect another section of transmission line, and the characteristic impedance of this transmission line is not equal to 50 ohm. It's not equal to Z sub 0. It's some, well, ZQ, something. Well, let's try to draw this.不对，注意哦，左边跟线的左边右边不太一样哦，所以这是在接线之前我看到的就是 Z2， OK。So if we connect a section of a transmission line system that happens to be a quarter wavelength long, then what is the property of Z1 over here? Well, according to this plot, we know the product of Z1 times Z2 equals to ZQ to the square. Okay? And we know that Z2 is a real number. Well, you deliberately rotate your input, your reflection coefficient to become a real number, right? So Z2 is a real number. ZQ in general is a real number. So Z1 must be a real number as well. And what is the value of Z1? Well, we know that it needs to be Z sub 0, the characteristic impedance of your original transmission line system. Then, what is the number of ZQ? ZQ equals to the square root of what? Z2, Z2 除以 Z0。卡住了 ，OK。是吗？不对，写错了。等一下，奇怪啊，今天有点卡。啊，这把 Z1 跟 Z0， 把 Z2 跟 Z0 的乘积开根号就是你的 ZQ 嘛，哦。And this is not the only solution, because we have another solution that is moving your reflection coefficient to reach the voltage minimum. So here you will have a minimum input impedance that is a real number. That is a real number smaller than Z sub 0. Here you will have an input impedance Z greater than Z sub 0. Okay, so you always have two solutions. So which one is best? Well, they all shall do. They are all legitimate solution, all valid solution. It depends on how convenient to change the characteristic impedance of your transmission line. Okay, so suppose Z sub 0 is 50, and the Z2 here is 100. Then what is the ZQ value? 71, right? So if this is 50, this is 25. then the ZQ value is something about 32 or 33, right? So it depends on which one is easier to make a transmission line of a 71 ohm or 33 ohm. It depends, okay? But they are both valid solution. Sometimes I will choose, for example, for this case, in general, I will choose this solution because the DQ length, DQ size can be smaller. Otherwise, if you choose this solution, DQ size may be larger. So, well, that's an engineering problem, okay? But they are all legitimate solutions. So let's keep on, okay? So the DQ value can be found using this equation. So it equals to lambda over 4 pi times theta plus pi, theta plus 180 degree. Well, this is the solution for this solution. This equation is corresponding to this solution. Okay, so that's the reason why you have this, in the small parentheses, you have theta plus pi. This is the phase change you need to accumulate along the transmission line. Okay, so theta is the phase of your reflection coefficient. And the pi is resulting from the fact that you want to reach the voltage minimum position. So this equation is the impedance at the voltage minimum position, which is which you have well, gamma r, the magnitude of gamma r is a fixed number, as long as you have fixed the value of the termination. But anyway, for this solution, you will have minimum voltage. You will have the smallest real input impedance. You will have the smallest input impedance, which is also a real number. Then the value of ZQ can be found like this. Okay, so Z sub 0 stands for Z1。所以第一个 Z0 指的是 Z1， 这边看到的 Z1。第二组呢其实是这边看到的 Z2。那它们因为间隔1/4个波长，所以它们的乘积会等于中间那一段传输线的特征阻抗的平方值。OK， 那 Z1 我们知道要等于 Z0 嘛。那 Z2 呢，根据你的伽马 R 来去计算，然后所以这里头都是已知啦，所以你的唯一的未知数就是你的 ZQ 值，但是是可以被找出来的，所以下面的式子帮你找出 ZQ 值，而上面的 7.41 帮你找出 TQ 值，第一个那个线段，但是这一组答案其实是满足那个你的那个 Z2 的那个阻抗是小于 Z0 的实数这一个条件的，所以我们有另外一组答案。这一组答案呢，就是 DQ2 的话，这边有点简单，它把 DQ1 加1/4浪，然后减1/4浪吧。But anyway, DQ both DQ1 and DQ2 will be two numbers smaller than half of wavelengths, because you will have two solutions in one revolution. 在转一圈的过程当中，你会遇到两个解，所以转一圈是最多转多少？半个波长嘛。所以这两个解都会，它的长度都会小于1/2波长，而它们刚好会差1/4波长，因为本来的起始点就刚好站在对面，所以 DQ1 知道的话，你把它加1/4浪达，或者是减1/4浪达，你就可以得到 DQ2 了。那以这边的例子来讲 ，DQ2 的位置呢，你会得到一个 voltage maximum， 也就是得到一个 Z2 的值比 Z0 还要大的实数解，所以它的那个 ZQ 值呢，就会介于 Z0 跟 Z2 之间啊，也会大于 Z0 就是了啊。所以这个式子跟前面那个式子差在这里啊，这边是上面是加，下面是减，但前面那个答案是上面是减，下面是这加啊。所以 7.44 的答案，你得到的 ZQ 会比 Z0 大啊，因为后面开根号的部分大于1，可以吗？好，那这是 ZQ1。所以这边有个所以其实 quarter wavelength transform the design of a quarter wavelength transformer is straightforward. It's straightforward and not difficult. But there's one problem. The problem is you need to be able to change the characteristic impedance of the transmission line. For example, if you want to match 100 ohm with a quarter wavelength transformer so that the input impedance can be reduced to 15 ohm, the characteristic impedance of your quarter wavelength transformer should be what? 71. So which means you need to be able to come up with a transmission line characteristic as 71 ohm. So let me ask you a question. If you have a transmission line type of coaxial cable, and you have another type of transmission line as the so-called microstrip line. Microstrip line. 微带线。Which one is applicable for the equivalent quarter wavelength transformer technique? 我们现在讲的1/4波长阻抗匹配转换器可以用哪一种比较好实现？用 microstrip line 还是用 coaxial cable？ 理论上啊，两种都可以啊，但实务上 quarter wavelength transformer 就不太可能用 coaxial cable。为什么？因为你一般假如我们都是50欧姆的系统的话，你要想办法生出一支70欧姆的 coaxial 嘛。那70欧姆的coaxial要怎么改？你要去改变那个内径跟外径的比例。好，那你可以跟那个电缆公司说，老板，我要1公尺长的70欧姆coaxial cable。那经销商会问你说：“你去吃大便好了。” OK。当然了，你就说我要10捆那个10公里长的那个coaxial70欧姆的coaxial cable。那经销商说：“好，是的，老板，我马上去下 order 哦，可以啦，你 customize 做是可以的啦，哦，但是那个量要够大嘛，对不对？啊，假如是 microstrip line 的话嘞。”改一下它的那个线径就可以改出来了，好，所以 quarter wavelength transformer 相对看起来 microstrip line 比较方便做，好，所以也就是说我们在传输线系统上面所学到的一些设计方法哈，其实也是要看实物的啦哈，所以像这个的话。左右两边是不同的 case 啊，左边是一个 patch antenna 微带天线 patch antenna， 那你会看到这个是天线呐，然后电磁波的讯号进到这个 patch 之后，它在上下叠合的共振腔共振，然后电磁波从旁边漏出来，而那一根细细的线是所谓的 transmission line 传输线啊。然后来去提供天线结构，电磁能量。那你会看到它是哪一种传输线 ？microstrip line 嘛，微带线传输线嘛，哦。那你会看到它， 为什么它一开始的那个宽度比较大，到后面比较细？为什么？它其实就是一个 quarter wave length transformer。好啦，我要问你的问题是，前面那段粗的阻抗比较大，特征阻抗比较大，还是细的特征阻抗比较大？特征阻抗怎么看？在传输线里头，单位长度电感除上单位长度电容，所以粗的线的电感性比较大，还是细的线电感性比较大？细的嘛，对啊，有信心点啊，没错啊，细的比较大嘛，所以你会看到粗的那一段，它的那个特征阻抗其实应该比较小，细的应该比较大，实际上答案也是啦，因为 patch antenna 只要你从边边汇入的话，它的输入阻抗大概是120欧姆，大概120欧姆。然后后面那段传输线，你大概 pretty sure 它是50欧姆。为什么？我有接后面的 transceiver 嘛，所以你需要有一个 quarter wave length 来去做到所谓的50到120。所以用 quarter wave length transformer， 你只要决定好它是什么，1/4波浪场啊，那你又知道你的那个输入阻抗大概是120欧姆。当然啦，假如这个东西假如挂虚部的话，会比较麻烦一点。不过我印象中好像差不多是10部啦，10部就120左右。所以你的 ZQ 中间那一段传输线的那个阻抗是多少？靠算数而已啊，6000开根号嘛，对不对？所以是多少？6000开根号是多少？780哦 ，OK， 好了，780啊，差不多了啊。那后面的话是比较稍微再复杂一点它是1/4啦，1/4，但它其实也都是红色的部分，大概是 quarter wave length transformer。好吧，也是类似的原理，让它去达到阻抗匹配好，那接下来 ，so let's move on to see the second technique, single stop matching. So as you can see here in this figure, the most prominent feature of single stop matching is this. This is referred as the stop. It can be formed with a short stop or open stop. But in the textbook, we usually adapt the form of short stop. Why do we use a short stop? Because with a short termination, and by changing the length of the short terminated transmission line, you can create any inductive loading or any capacitive loading. Because short stop itself does not absorb any energy, so all the incident signal is reflected, so it has a reflection coefficient of 1. It has a reflection coefficient of 1, and what? And unless the length of the short terminated transmission line is a multiple of quarter wavelengths. Otherwise, the input impedance of this transmission line will become a fully reactive load. So the impedance is purely reactive. It can be a positive value or a negative value according to the length of the line. So anyway, the short stop can help you create any reactance. You only need to change the length of the short stop. And so in this configuration, we have a few knowns. We know what? We know the Y1, we know the admittance required, which is what? What is the value of the admittance required? If the characteristic impedance is 50 ohm, what is required Y1? 0.02, right? 1 over 50啊。注意，我们现在用 Y 哦，我们现在用 Y 不是用 Z 哦。为什么用 Y 不是用 Z？ 为什么？并联，对，因为你看到的是，你往右边看到的主干道它是传输线嘛，而你的 short stop 是以并联的形式跟它结合在一起，所以你要在计算它的等效输入的值的时候，是看输入导纳，也就是 Y 值比较方便，就两个左右两边的 Y 加在一起就好了嘛。好，假如你用 Z 的话有点麻烦。OK， 所以我们用 Y， 所以你知道 Y1 应该是多少？好，但注意啊，我们昨天最后讲的时候有分大写 Y 跟小写 Y。好，大写 Y 是绝对值，小写 Y 是正规化的，所以这边用的是小写 Y1， 所以是正规化的。好，所以它其实应该多少？1，好不好？1啦。好，正规化之后就是跟谁正规化？跟那个 Y0啊，来去正规化，所以我们知道 Y1 应该要等于1，然后 ZR 是你的负载，所以 well suppose 你也知道。那你要决定的是什么？你有两个未知啊 ，there are two unknown to be determined。One is the length of the short stop LOS. Well, you don't know what kind of the reactance. Well, is that reactance? Well, that's JB. 从这边看进来的那个输入的导纳值是 JB。B 其实就是电纳，纯的电纳啊，应该叫做英文叫什么 ？Susceptance 啊。那再来是那个 DS。也就是你要在哪里把那一个 short stop 接上去，啊，所以那个 short stop 应该接到哪里？我们可能看下面的说明哈，来去看说 DS 要如何决定 ，LS 要如何决定啊？所以在这个设计里头 ，Y1 跟 ZR 是已知，未知是 DS 跟 LS。当然了，其他还有一些已知啊，比如说。这个传输线基本上都是同样的传输线，事实上这一段跟这一段并联这一段都是一样的传输线，啊，所以这个做法这一种做法对于那个我们刚才讲说口维修 cable 来讲，这个就比较适合口维修 cable， 因为它的那个传输线的特征阻抗或特征导纳都不用换，都可以是一样的，好，那你只要决定长度跟并联的位置。啊，所以对于口维修 cable 来讲，就比较好做，所以你可以使用同型的同阻抗的传输线，调整并联短路线段的位置，啊，也就是 DQ 啊 ，DS， 对不起，这边就用 DS， 还有它的长度就可以达到匹配啊。So for single stop matching, one stop is used, and the match can be achieved by varying the location of the stop, as well and the length of the stop. So we assumed the characteristic impedance of the stop to be the same as the rest of the line, and we also know that for lowercase z and lowercase r, they are normalized impedance and normalized admittance. And B is the normalized input susceptance of the stop. 正规化导纳。So we will begin. So to solve this problem, we will begin from the left. From the left. 等一下，好像下课了。我这边怎么扯太久 ？OK. We'll begin from the left. So we know that the goal is to achieve that y1 equals to 1 plus j0. Okay? And y1 will be the same as y1 prime plus jb. Right? 我们先停一下好了。Okay, so we try to solve this problem in a reverse order. So the goal is to achieve the normalized admittance as 1, which is y1. y1 equals to 1 plus j0. So it's purely resistive, and the admittance is the conductance, the normalized conductance should be 1, and the susceptance should be 0. And on the interface, on this dashed line, we know that y1 is what? y1 equals to the sum of y1 prime and jb. Y1 equals to y1 prime plus jb. So therefore, y1 prime, which is the input impedance from the right of the dashed line, equals to 1 minus jb. 1 minus jb. And what else? What else? So y1 prime, the normalized admittance is 1 minus jb. The reflection coefficient at the right of the dashed line is gamma 1 prime, which equals to, by definition, equals to 1 minus y1 prime divided by 1 plus y1 prime. So you substitute 1 minus jb in here, you end up with the reflection coefficient gamma 1 prime equals to jb over 2 minus jb. So jb, what is the phase of jb? 90 degree. What is the phase of 2 minus jb? Well, I need to know the value of b so that I know the phase of this thing, right? But what we already know is the magnitude of the reflection coefficient, right? Once you know the impedance of your termination, you can calculate gamma r. And gamma r can be translated into gamma 1 prime by knowing the distance of the first section of the transmission line, which the distance equals to ds. And the phase change associated with ds is 2 beta ds, exponential j 2 beta ds. So the magnitude of this number can be replaced with the magnitude of b over the square root of 4 plus b to the square, right? And this number equals to gamma r, okay? So once you know the magnitude of gamma r, you can use this relationship to find the magnitude of b. Well, and the only problem, so the next problem is how large, what is the length of the shortstop, LOS, so that you can create B, so that you can create this subacceptance. Another question is, what is the distance to make this, to connect the shortstop to the main line? And the problem can be solved by knowing this thing, identify this thing. We know that this is the total phase of all these components in the formulation of gamma 1 prime. So that will include 90 degree for the denominator JB. That will include the phase of 2 minus JB. So we represent it as arctangent of B over 2. And that will include the length, propagation delay of the length as well. So here you have 2 times beta times ds. And we know that the solution will repeat itself for every half wavelength of the revolution. So we substitute with a 2n pi. So that the solution can meet the requirement. But anyway, we will limit. We will not adopt a solution with a too large ds. We try to we try to limit ourselves from choosing a DS that is smaller than half a wavelength 啊，也就是说你的这个 DS 的长度解，一般合理来讲就是选在半个波长以内啊，因为你超过半个波长，其实反正你最短的 solution， 你在半个波长里面你就会找到答案了。事实上是在半个波长以内你会找到2个答案，啊，跟那个 quarter wavelength transformer 一样 ，short stop matching 你也会有2个答案，啊，你会有2个答案。那这2个答案的那个 DS 其实会差半个波长吗？不会，不一定，不是啊。你会有2个 DS 的解，还会有2个 LS 的解，也就是那个 short stop 的解。所以在这一页里头我们再看一下怎么样去求解啊。So this thing is given the reflection coefficient of this terminated transmission line. We know the magnitude, we know the phase of the reflection coefficient at the termination. Using the magnitude of the reflection coefficient at the termination, we can know the value for B, right? So by manipulating this relationship a little bit, you can find out the B value. You will have 2 solutions. One is greater than 0. One is smaller than 0. Which means you will have 2 solutions. One is making this short stop as an inductive stop. That would be a JB value that is greater than B that is greater than 0. If B is smaller than 0, the short stop input impedance of the short stop will become capacitive. 我这边讲的不是很精确对不起，因为我还是用那个 Z 的想法在想，所以那个 B 值大于0跟小，应该说，假如你用 Z 值来想的话 ，Z 是 R 加 JX 嘛，所以 X 角正值的话它是电感性，负值的话是电容性。那这边我们看的是导纳的那个 B 值啦，所以 B 值假如是正的话，应该是电容性吧，负的话应该是电感性，不过 anyway， 你会有2个 solution， 而这2个 solution 刚好它的 B 值是一正一负，好，那 B 值的大小从伽马 R 可以找的，伽马 R 的大小可以找得出来。好了，那下一个比较麻烦的是那个 DS 值。下一个比较麻烦 DS 值，那一样用前一页所看到的 solution 的形式所以这边你大概有些自由度来去选你会去选一个 DS， 然后这个 DS 基本上应该要落在这个范围，大于0嘛，对不对 ？DS 不可能小于0吧，对不对？对，小于0不是不合法的嘛，所以一定要大于0。再来呢，你一定会在半个波长内就找到这2个 DS， 所以 DS 的值应该要小于半个波长，只要你算出来的值超过的话，你就自己扣自己扣半个波长下去因为每隔半个波长它会重复一次所以把这个相角 DS 值呢 ，DS 的长度其实它 DS 的长度其实就是那个相位乘上 lambda 除以4派，就是它的长度了这是长度跟相角变化的关系。所以我们把这个相角变化的关系丢进来这边用就是了所以根据 B， 所以这里头这里头其实有哪些变数，或者未知数，还是哪些已知数？曼达已知西塔已知B 的话从这边得来，这边先解完 B， 这边 B 就已知。N 的话就是拿来凑的，让它凑出来说你的 DS 是落在半个波长以内，所以这里头 N 是你可以拿来凑的了这 N 可以随便决定了好，所以我们这边看了finally to find the solution for the short stop length, okay, so in this slides we know the number of B. Once we know the number of B, we can derive the length of the length of the section. We can find out the position to connect the short stop. So DS is the first solution, is the first information about the solution we need. And actually you will have 2 DS because you have two solutions for B. One is a positive and the other is negative. So once the DS value are determined, you can try to solve for LS, which is quite straightforward because you need to adjust the length LS so that the input admittance equals to the required B value. And we need to change the equation a little bit because originally we introduced the input impedance for a short stub line as J Z sub 0 tangent beta L. So J in will become 0 if L is 0 or multiples of half wavelengths. Z in will become infinite, become a large number if beta L equals to odd multiple of pi. 所以根据贝塔 L 值贝塔 L 假如是0正负2拍正负4拍的话，那它就等于 short。那假如它等于13579拍的话，它就等于 open。那只要不是拍的倍数，那它就是正 J 或者是负 J。Okay? So we first normalize the expression of 7.13 like this. So by dividing both sides with Z sub 0, you end up with the normalized impedance as J tangent beta LS. And taking the inverse of Z in, you end up with the you can find the relationship between the normalized susceptance B and the length LS. So tangent beta LS equal to minus of 1 over B. Then you can manipulate this equation a little bit to find out the solution for LS. So the first solution is lambda over 2 pi times arctangent of minus 1 over B, then plus half wavelengths. So LS must be a positive number because it's a section of transmission line. And LS should be smaller than half a wavelength to find the fundamental mode solution for this. So this is a solution for B greater than 0. This one is for B smaller than 0. But anyway, you can find out the analytical solution for LS and DS. Okay. The problem is a little bit你觉得这个推导好记吗？当然，这样你类似题做10次，你大概是会记下来嘛，对不对？也不是说完全记不起来嘛。事实上，每年考试的时候，我基本上都希望大家透过 Smith chart 的作图，帮我把答案找出来。但结果都是大概蛮多考高分的人就直接用关系式就给它解出来了OK 所以你直接硬背硬记也是可以啦毕竟它还是一个 make sense 的流程但我们接下来就跳过